Okay. Hello, everyone. Good to start this. Yeah, I'm Hendrik Kolvenbach. I'm part of the Robotic Systems Lab of ETHZ. I'm going to talk a little bit about some of the approaches we've been investigating with legged robot for exploration in the past and also recently, and what we think is the future. I also put some lessons learned there because I thought it's nice to have some insights. Yeah. So this slide is, some people have already seen this. There's a couple of opportunities for legged robot in exploration. First and foremost, that we have different gravity depending on where we go. So we can make use of efficient walking patterns for these different gravity settings. Then we have an environment that's highly diverse. So you have areas where you have, for example, flat terrain, but then you encounter areas like here in the Victoria crater, which are really steep, very cluttered, but scientifically very interesting. So these are certainly areas that we want to go with the robot. So you need to have a system that's capable to do it. Furthermore, we have these areas like here, these caves on the moon, for example, that we want to investigate, yet we don't really know what we're going to see there. So we'll have a system with a certain like very high versatility to be able to navigate these environments. Lastly, a limb system also can use its limbs basically to investigate, probe the environment. That might give you an advantage as compared to like highly articulated systems. So I want to start with this quickly. This is something that I launched after my PhD, because when we did the PhD, I was coming from these like 6 tiles basically. And I was like, as a researcher, you start thinking, okay, we could do this, we could do this, we could do this. But in the very end, you have to have somebody who makes use of the system, right? We don't build robots just for the sense, make building robots, but in the end, you want to have them doing something useful. So this was a project with ESA where we investigated a particular area on the moon. The Aristaeus Plateau is geologically very interesting terrain. And I wanted to understand really what are the requirements in this environment. So we went a bit further. You don't need to understand what the symbols are. Like these are interesting scientific targets. We try to cluster it, added some things like what would be relevant for a mission, like landing ellipses, etc. And then we investigated which system would make sense to use in these areas. Then we didn't want to go with a traditional wheel system. So we went a bit further into basically the areas where you would need a legged robot. We did this effort primarily to really understand what is it that we can provide extra in comparison to other systems. So what came out of this is like highly sloped terrain, 15 degrees, 20 degrees slopes, and also cluttered environments, and also areas where you have to navigate certain fractures. So that just to set a bit the motivation. In the meantime, then we have developed technologies that can actually overcome this type of terrain. So if you might play the videos, we started with the things in the top left, very basic experiment on a tiltable terrain, where we started to go up and down the terrain. And then in the other videos, you see more recent works currently under review, where we try to go in even higher environments and also adding payloads on top of the robot in order to overcome this. This all came together then in around 2020, 2021. There was this push towards the moon, I would say, like more and more people got to know that there are these landers coming up, these opportunities. And ESA was asking the community, what can we do? What can we bring on such a lander? Still it's not completely answered this question, but amongst this, what they also launched was this Space Resource Challenge that my previous speakers already shortly touched on. So the goal of this challenge was to get a bit of setting, was to find and analyze resources in like in an unknown terrain in a limited amount of time. And I think this is also the most important requirement in a way that also motivated later on to use a team of legged robot, because very short amount of time and lots of things to do. So either you have like a super capable robot or you bring a couple of robots. We also had to map it. There was some delay. They had a low angle illumination to make it a bit more spicy. And then we had no visibility of the robot, so we had to rely on what the robot sees. So this was the terrain. And the second challenge, we didn't know this terrain until we started the robot in the starting area. So there was this curtain that lifted, and from that point onwards, it was only what you saw through the robot, basically. So also we formed a team. We used legged robots for this and teamed up with some geologists that helped us selecting a certain set of payload that makes sense. For the first round, we basically duct taped everything to the robot. We had one robot here. We can see here a microscopic imager with some zip ties in the front of the robot, and then also a Raman spectrometer in the back. And then here a sensor payload, basically a pen and tilt unit with some zoom cameras. This was our system, and the system had like mapping capabilities and had means to investigate interesting areas. This is the video we got after it. David, if you can. This was the first set. This was this resource-enriched area, as they called it, with these rocks. And before that, they had an area where you had to traverse in order to get there. So you can see it was not super challenging to traverse. Yeah, they built up some ramps. And then once you were in this, like, once you found the resource-enriched area, you had to investigate the rocks. So we got some results from this. So part of the challenge was also that you had a limited time to actually process all this data. And in the end, you were graded on the report that you handed in. So we did some quick extraction from the mapping pipeline and some pictures, and that was good enough. So we could proceed to round 2. So for round 2, as I said, you have to map this area. You have to find many resources, and you don't even know exactly what type of resources. So our idea was here to go with a team of robots. One being a scouting robot, which primarily task was to map quickly the environment, report this back to the operator so that he can select scientifically relevant targets. Then we had the scientist robot here, where we updated our previous robot and mounted the spectrometer and the microscope on the robotic arm to be able to do really like contact science, basically. Then we also had this hybrid robot, which was basically there for means of redundancy. In order to maximize the payload utility, we also had to develop some tools. Some of them are currently under review and hopefully be published soon. But of course, if you have a diverse set of skills, you have to find a way to utilize and make the max out of this, right? And this is part of this pipeline. So again, I don't have much footage from the robot itself, but this was basically how it went when we went to the challenge area. I think it's a super nice video because you can see really 3 robots working simultaneously. Sometimes it's a challenge to get one working, but now we had 3, and this was really cool, I think. After the challenge, now disclaimer, we had this footage where the robot is walking on the terrain. It was not particularly challenging terrain, I have to say. Like, we were a bit disappointed in that regard. Here we can see during the challenge, the mapping. So the robot was incrementally mapping the terrain and sent back small amounts of data just to keep the throughput relatively low. And then here we also had some help, of course, in identifying relevant targets. And we had 2 operators, and our operators were quite busy as compared to Tristan. So maybe quickly to the results. So we had all 3 robots operating on the terrain. Interestingly, here you can see like some had a lot of scientific return, especially taking spectra, which was interesting for us, and also taking contextual images was good. And then also we had like a large set of scientific investigations. Again, we had to write a report in a relatively short amount of time. And here comes one of the challenges, in my opinion, when you have more robots, because in the end, you generate really, oh yeah, there we go. Because we get this massive amount of data. So we had like numerous pictures, data overview pictures, and in the end, that resulted in a 220 pages report that we basically had to build on the fly after the challenge. So if you have a diverse set of robots, we clearly underestimated how much data this system actually is then producing. I think this thing stopped working. I think my laptop died. Okay. Yeah, so here quickly my thoughts on this. So I think the team is absolutely great to maximize the science outcome because you can parallelize, right? So you get way more broad, you can just sample more points just because you have more robots. At the same time, it allows you to go more in depth because you have a diverse set of skills, which means that you can now really add more instruments in a specific domain and really target that area. It also gives you the redundancy aspect, so you don't have single point of failure. If the other robot would have died, that would have been 0 points, right? If one of the other robots would have died, it wouldn't be not only let's say one third less, but maybe could still do 100% of what we were intending to do. And you can really profit from the synergies. So for example, if you have more targeted robot, like a robot that only goes for mapping and reports this back, of course, it's better than having a robot that has to do both at the same time. Future work that we see, I stole this from a proposal that we did together with DLR and some others, was to create even a more heterogeneous set of robots. What I showed before was all legged robots, but what we are intending to do is to go more and also have different skill sets. For example, having a flying robot for mapping, maybe it's more optimal. So we can get definitely some increases here. Then also we want to increase the autonomy in task creation. So basically identifying scientifically relevant targets. You saw some gist of it already before, where we did the instant segmentation of the rocks, but you can do way more in order to really get a defined task in the end. And then the task allocation, basically, how do you schedule all of this? What was already nicely done in the autonomy stack of FZI is something that we were not having. So basically there was still a user there that had to then select what is actually doing. And then if you come from both ends, from the task, the creation and task allocation, then in the end you have a nice full autonomy stack, in my opinion. I quickly touch on this slightly different topic, but it's really at the heart of my research. So I really would like to present this because ultimately what we're aiming for is technology that can go to another celestial body, right? This is the main goal, at least for us. And so in order to do that, especially with disruptive technologies like legged robots, is to come up with technology demonstration mission. So in 2021, we launched this project with the goal of building a small-scale legged robot. This is a system which is relatively lightweight, it's 6 kilo. Launch costs are expensive, so you try to make it lightweight, make it small, so it can fit on a large variety of landers, and then use this to demonstrate the technology. Yeah, that's a rendering, not the reality yet. What we use there is also another technology besides the legged robot, reinforcement learning, also very popular nowadays at the conference, of course. So we train the robots in simulation and learn highly dynamic gates. This robot initially was set for an asteroid where, because of the very low gravity, this type of jumping gates make a lot of sense. So we also, of course, did some, let's say, low fidelity tests in the lab. I think those you have to play. So there we also trained 3D reorientation, of course, in a gimbal system on Earth. Everything else is very expensive. But then we want to push this further and also validate this in a relevant environment. So, no, there was, yeah, no, it's okay. Yeah, basically, and then built on two sides. So what I see is basically our main two roads that we want to push for is this teamed autonomy, basically having heterogeneous sets of robots, figuring out how do we generate more science on site. And then on the other hand, being able to demonstrate the technology also in space. For this, we put in a number of proposals. So proposal stage, so none of them, except for 2 of them, they are not confirmed yet. But that's just saying that we are serious about this and want to push this further. Some learnings that I found relevant for this is that I think it was super beneficial for us to add also scientific stakeholders in the very beginning to really make a clear motivation of why we're actually doing it, in order to get like also more sustained funding for the activities and also, let's say, more support in general. It also helps you a lot by defining the mission scenario more clearly. Then what we learned was very important is to include the operations early on, especially when it comes to, let's say, report writing in the end, like this kind of stuff. And also really to apply the 80-20 rule. So we see like, okay, we have this problem, and instead of going super broad in the future development, let's select the solution that actually works and start building bottom up on this. Yeah, testing was very important for us. So we had test sites very close by where we could regularly go and really learn a lot. So the second and third point, I think they really go hand in hand. And then another big challenge, especially when it comes to sending something to space, in my opinion, is like somehow bridging this TRL dev valley between like research and having something in space, which is a lot of engineering work. So it's very costly, but it doesn't generate papers necessarily. So finding people that are willing to support this is a bit of a challenge. But I hope that now with the new landing opportunities coming up and decreasing launch costs, that maybe there's a bit more of a push for this. So of course, I'm not doing this alone. There's a large team behind at the Robotic Systems Lab. They were striving for making robots work for unstructured and challenging environments. And with this, I would like to conclude. Thanks a lot.
Thank you, Hendrik, for the impressive results in the presentation. Questions for Hendrik? Yes. Yeah.
Thank you very much for a great presentation. So I have a question for the first part of your talk. And so you mentioned at the beginning that the advantage of the legged robot system for the challenging environment. But for the ESA's resource challenge field that you have some soft soil environment. So then I believe that the locomotion on the soft soil environment using legged system, not that easy. So then just please let us know that if you have any observation or any learning things from your challenge.
Yeah, I mean, in my opinion, the interaction with the soil, like mechanically, is a very hard problem because it's not something you can easily integrate in a simulator, let's say, and then have the robot learn a controller on this soil. I have to say though that in this particular challenge, it was not too much of it was not too difficult because they used relatively rough granular material, and I think none of the teams really had big problems with this interaction, in my opinion. And also that's why I showed this climb on these climbs on this like inclined soil. I think that's still one of the more challenging problems, because especially if you go on a like inclined sandy terrain, you have all these shear effects which are even more challenging to model. So I think for me this is really the benchmark, like how high can we walk up.